Hello, everybody. It's great to be here. So today I'm going to talk to you about Shapeless 3 and the new type class derivation features that have landed in Scala 3, which were designed alongside Shapeless 3. It's been a really kind of exciting, long and exciting journey to get from where we started out. I guess in Scala 2, struggling to get some form of type class derivation working. This was the work I did in Shapeless 2, and it was a huge and enormously exciting opportunity to be able to work with EPFL to make the experience of that better. For people working with Scala 3. Anyway, Shapeless 3 is what has come out of that, alongside the type class derivation primitives in Scala 3. And I'm going to introduce you to some of those right now. Okay, so we're talking about type class derivation. First, it would be helpful to get clear about exactly what we mean when we say type class derivation. Type class derivation is a mechanism for automatically inferring type class instances for an algebraic data type from solely the statically known to the compiler structure of the algebraic data type, and from any instances for component types of the algebraic data type that we might have defined ourselves, have available in the environment in some way or another. Okay, unpacking this a little bit with an example. This would be in the new Scala 3, shiny Scala 3 syntax, a definition of a traditional show type class. The type class is indexed by some type T, and it provides a show method which takes an argument of type T and turns it into a string. Very unexciting, but it's going to give us enough insight into what's involved in type class derivation to be able to get some kind of purchase on the idea. Okay, so you can provide instances of this type class for primitive types. I'm not going to show the implementations of these. It's completely trivial. A show for an int is obviously going to turn an int into a string. A show for a string is an identity. A show for a Boolean is, again, a trivial piece of code. What's not so trivial, though, is if we want to write a show for a case class, a product type, which consists of a number of components. This particular one, it's got an int, a string, and a Boolean, and is unimaginatively called ISB. It would be very nice if the compiler could somehow or other help us synthesize a sensible value for the type class instance corresponding to show ISB. It knows everything there is to know about the structure of the type, and it knows everything, and it has instances of the type class for the component elements of the type. So it feels as though it ought to be a simple mechanical type-driven process to summon up an instance of the type class for the whole case class. So Scala 2 has no built-in mechanism for doing that. Shapeless 2's raison d'etre in the end turned out to be pretty much to provide that kind of type class derivation support for Scala 2. It works well enough. It's used all over the place, but it has a number of fairly fundamental issues, both in terms of compile time performance, runtime performance, and I suppose more fundamentally, the mechanisms that it exploited to be able to work with the structure of types at compile time relied very heavily on internal implementation details of the Scala 2 compiler, which meant that there was really no possibility that I'll qualify that later. There was a very serious question mark over whether or not Shapeless 2 in its current form would be able to make it across the divide between Scala 2 and Scala 3, which is essentially a completely different compiler with completely different internals, which couldn't be relied on in the same way that they had been in Shapeless 2. Irrespective of whether or not actually forward porting Scala 2 to Shapeless 2 to Scala 3 turns out to be possible, there really are a number of reasons why I think it would be desirable to come up with better tools for doing this. A lot of what Shapeless is doing under the hood is really very, very unpleasant, and it would be much nicer if we had officially supported mechanisms for doing those kinds of things. So Scala 3 provides those officially supported mechanisms. It has a number of directly supported primitives. It has the concept of a mirror type, which we'll come to next, which is essentially a compiler representation of the structure of a component of an algebraic data type. It provides some new syntax, a derives clause, which can be attached to the definition of an algebraic data type to indicate that it is expecting the compiler to orchestrate the construction of instances of named type classes for that algebraic data type. We'll see that again in a little while. And then it has a convention-driven mechanism for, as it were, collaborating between the algebraic data type for which type class instance is being derived and the type class which provides a recipe, which in conjunction with the compiler primitives can be used to construct the type class instance. These things are intentionally very low level. And the idea is really to provide a minimal framework which allows higher level libraries to be built on top of these primitives to provide a rather more sort of ergonomic end user experience for type class derivation. There are some other kind of more technical reasons why the primitive nature of the very low level nature of the primitives is desirable, and we'll touch on those in a moment. Okay, so first of these primitives are mirrors. Mirrors are they're a generic programming primitive. They're defined for all Scala algebraic data types, and that includes sealed traits and case classes. So this is the traditional way in which in Scala 2 we're used to defining algebraic data types. But they're also defined for algebraic data types defined using the new Scala 3 enum syntax. They support algebraic data types of all kinds. Now, when I say kind here, I mean kind in the type theoretic sense, and we'll see how that is quite a significant extension in capabilities over what has previously been possible in Scala 2 with Shapeless 2. And as I mentioned before, these things are intentionally very, very low level. So let's see what a mirror looks like. A mirror is essentially a sealed trait containing a collection of type definitions. The type definitions that we have are things which are going to map between the type that we are reflecting on, namely the components of the algebraic data type that we're trying to work with, and some related types which which are the ones that allow us to drive our derivation process. So we'll see in a little bit more detail exactly what these different components do. The hierarchy of mirrors splits into two, depending on whether we're looking at a product type or a sum type. So a sealed trait, a sum, a case class for a product. The primitive term level operations we have here are an operation which allows us, given an element of, say, a sealed trait, to decide which of the branches, which of the distinct sealed, which of the distinct case class subtypes of that sealed trait or enum we're looking at. This is simply something which will map us to an integer index into which of the product types we're looking at. And in the case of a product, we have a mechanism for turning a very loosely typed Scala product into an instance of that type. Now, whilst the type definitions that you can see in the mirror trait will be very precise, the two term level defs here are not particularly strongly typed. And again, we will see some reasons for why this is the case. And if you're concerned about the lack of very precise typing here, don't be concerned, because the intention is that these are used as low-level primitives, and then they have a more strongly typed veneer layered on top. And in this particular instance, Shapeless 3 is going to provide that more precisely typed veneer. Okay, so let's take a look at an example. This is the case class that we were looking at earlier on. If we go to the Scala 3 REPL and we import the relevant package, and we attempt to summon this mirror, we specify the type we're interested in by defining in the refinement that we summon that the mirrored type is ISB, the type we're looking at, and the result that we get back will be a refinement of the product extension of the mirror trait with some additional type members specified. So the mirror type is the type of interest. The mirrored monotype, I'll explain a little bit more later about what the difference between the mirrored type and mirrored monotype is when we see an example where these two differ. The labels are the labels corresponding to the name of the case class, but captured as a string singleton type. So there is no actual value here. This is a pure type capturing capturing the string label of the case class. The mirrored element types are a tuple representing the types of components of the case class, and the mirrored element labels are again a tuple of string singleton types corresponding to the labels of the elements of the case class. So again, these are all pure types. There are no actual values here. The tuples of strings look suspiciously like a value, but in fact they're not. And this is quite an important feature of this design, because one of the things that we aimed to try and do was make the footprint that mirrors have as close to zero as possible. So bear in mind that the mirror infrastructure is something which the Scala compiler is going to be providing for every single case class, every single sealed trait with a companion object. This has to be something which is very, very lightweight. And what is more lightweight than a type? This is something which exists at compile time. It's something that we can work with at compile time using type-level programming techniques, using meta-programming techniques. But it doesn't leave a trace at runtime. So we can actually help ourselves to sort of a fairly rich budget of a type level components of these things, and make this a facility which is always available, as opposed to something which has to be explicitly opted into by the programmer. And there are a number of advantages for doing that. Making the mechanism opt-in would make the ability to use type class derivation in general contexts sort of very hit and miss, and it would depend on sort of third-party decisions about whether these things have been opted into or not. So let's take a look at another example. This is an enum. Here we have something which looks a bit like option. It's described as defined as an enum. We have an option type. It has a single type parameter. It has a sum and a none. In this instance, we can see something interesting about the design, namely that the kind of the mirrored type that we use to summon the mirror now actually corresponds to the kind of the data type itself. Now this is something, so again, you can see that the kind of mirrored type in the monomorphic case, it's just a type of kind star. In this polymorphic case, the type of the mirrored type is a type of kind star arrow star. So immediately now we've got something where we're actually looking at a polymorphic mirror corresponding to a polymorphic type. Now, if we compare the definitions between the two cases we've seen so far, you can see the way in which things vary here. So we can see that we have the type constructor, the opt type constructor is threaded through the mirrored type and the mirrored monotype. And here we can now see, if we compare with the previous case, that there is a difference between the mirrored type and the mirrored monotype. The mirrored type is polymorphic, like the underlying data type. The mirrored monotype has all of its holes filled. It has been monomorphized. It no longer has any polymorphism. And this is important because this is going to be used in conjunction with the sort of erased underlying infrastructure that we'll be using to work with terms under the hood. And if we go back to the definitions of ordinal and from product, you can see that these two things are defined in terms of the mirrored monotype. And this is quite important because you'll notice that these are term level definitions which must be implemented by single values. It would be impossible to have these things be polymorphic over all the different kinds of data types that we might attempt to do some kind of work with in a type class derivation way. So we need to be able to have some kind of abstraction, or some kind of abstraction over types of all kinds. There isn't really one in Scala 3, even though it has some limited forms of kind polymorphism. For now, we work with a monomorphized version of the polymorphic type. Okay, we can see from here then that we can see the way in which the type parameters of the ADT are threaded through the mirror. And we can also see the way in which, if we look at the mirrors corresponding to the product elements of the ADT also generate their own mirrors. Here, the sum is also polymorphic, so it has the same form as opt. None, on the other hand, is a monomorphic type, so it has a form which is more similar to the previous monomorphic type that we saw in the previous example. Now here we can see an example where we've actually asked for a mirror of the polymorphic type, but instantiated at some specific type. So this is now a mirror not for opt, but for opt of int. Now this again is now, because the type parameters have been fully applied, this is now a monomorphic type. You can see again that the mirrored type and the mirrored monotype are now identical again. Okay, so let's have a quick look at how some of this stuff works out under the hood. Here we have our simple case class, and we're just going to summon the mirror for it. So let's quickly compile that code. I have enabled the option which will show the compiler trees that are generated after type checking and inlining, which will show us exactly the form that the mirror is. Whoops, here we go. So here is the mirror that we've had generated for us, and you can see that its type has been expanded in the way that I described it. So here you can see that we have the monotype is ISB, the mirror type is ISB, the labels are a tuple the label is a string, but this is a type. The mirrored element types are in string Boolean, as they should be, and the labels are a tuple with singleton types corresponding to their elements. And the main thing I want to show you here is that this mirror is in fact the companion object of the case class. So what we're doing here, if you can see here, this is the definition. These are the trees of the companion object of case class ISB. You can see that the mirror is really just a type level veneer that has been painted on top of the case class. It adds no footprint at all. The only thing that we're going to see that is an additional piece of code which generates some kind of footprint is the definition of the from product method. And this is the absolute minimum that we need to be able to take some kind of generic thing, albeit very weakly typed here, and turn it into a value of the type that we're interested in. So let's just go back to this. I'm going to very, very quickly show you what this looks like in the case of a polymorphic type. So if we compile this again. So here you can see that we have, let's have a look. Let's find the, did I actually uncomment all of it? No, I didn't. Let's do more. So this is going to show us the, whoops. So this is going to show us the mirror for the polymorphic abstract type. And again, you can see here that we have the monotype, which has been monomorphized. We have the mirrored type. And again, we have the labels. What I'm going to show you next is what happens if we actually, let me show you this. Actually, I'm running dangerously low on time, so I'm going to skip this part and carry on. Okay, so these are mirrors. The next part of the picture are derives clauses. So derives clauses are new Scala 3 syntax, and they are annotations for ADTs, algebraic data types, specifying the type classes that are to be implemented. The compiler generates instances of type classes in algebraic data type companions, and there is a convention-driven interface between the type class companion and the compiler, which allows it to create the instances for the ADT. So take this as our running example. We have our case class ISB, and now we've added the this derives show. In our companion object for the show type class, we define a derived method. So what's going to happen is that the compiler will generate in the companion object for ISB a hidden lazy implicit value defining the instance for show for ISB, and it will produce that value by calling the derived method on the show type class companion object, providing the mirror for the case class as an argument. Now, if you remember, the mirror for the case class is the case class itself. So we're basically just going to be passing the companion object of the case class to the derived method of the show type class companion object. It will view that as being the mirror of the type, and it will be able to do something with the mirror to generate our instance. So I'll just give you a quick view of what that looks like. So let's have a look. Right, so you can see here that what we've had, so if we can find the various bits and pieces we have here, this is the case class companion object. And we can see that we've had defined for us by the compiler in here this lazy implicit given instance for the show type class for ISB. The instance is, as I said, constructed by calling the derived method on the show type class with the instance of the mirror for ISB as its argument. And again, as before, this is simply the companion object itself with the additional types layered on top of it. So there's really no footprint here at all. This is all just types. And in the companion of the show type class, we can see that we have a method here. So this is our derived method. This is the method that we've just called. It takes the mirror and it promises to produce a show of t, but as you can see, there is a triple question mark here. That is, if we go back to our code, that is the triple question mark we left here. So then I think the question clearly is, well, what is supposed to go in the place of that triple question mark? So I guess the temptation is to think that this is the point at which we draw the rest of the owl. Fortunately, there is actually a rather more detailed answer to how we can do that. If you wanted to work directly with Scala 3's mirrors, There is a description of how this process works using mirrors, inlining, and the various other direct Scala 3 metaprogramming mechanisms. But I think that unless you have fairly specialized needs, you will want to work with some kind of high-level library or other. Shapeless 3 is one, there could be others. The fact that we have a toolkit of parts in the Scala compiler means that there are many possibilities that people can explore. This is the approach that I settled on as part of the process of working with the Scala 3 compiler. Okay, so Shapeless 3 provides a number of components, really only the second of which I'm going to talk about in very much detail. So it provides a generic type class, which itself splits into a generic for products and co-products. These are very, very similar to the generic that people will be familiar with from Shapeless 2. The main difference is that these are generalized across kinds in a way that I was never able to manage in Shapeless 2. There was a sort of half-hearted attempt to get to types of kind star arrow star, so types with a single type variable in Shapeless's generic 1. But really, I wasn't. It was very, very ham-fistedly done, and it didn't generalize in any particularly nice kind of way. Horrible implementation under the hood. Anyway, this is now done in a very, very clean, systematic, generalizable kind of way. It's implemented directly in terms of mirror. In fact, generic are in a Scala sense direct refinements of the mirror types. They are basically mirror types with a few additional type members attached to them. More interesting part is a higher level abstraction which makes derivations of many types of type classes very, very much more straightforward. So this is something which will capture the type class instances of components of an algebraic data type and provide type-safe mechanisms for folding over them in a number of important ways, which make the construction of type classes for a large group of type classes really quite straightforward. It again is implemented in terms of generic and hence is also polykinded in the same way. So this is the generic, which I guess I'm not going to talk about a huge amount. This should look fairly familiar to people who have seen Shapeless 2's generic. Things get interesting when we start looking at the way it generalizes over type. So you can see this is generic for types of kind star, but we also have generic for types of kind star arrow star. This now corresponds to Shapeless's generic 1. This would be something that allowed you to, for example, define a functor type class derivation for a type like list or box, as I've illustrated at the bottom of the slide here. Types of kind star, arrow star. So these are type classes indexed by types which themselves have higher kind of type parameters. There are some really interesting examples of things like these, and you can use this to derive things like higher order functors, and which allow you, for example, rather than with vanilla functors where you map a function, here you can map a natural transformation over a data type, and there are lots of very interesting things you can do with those. And then also for types of kind star, arrow star, arrow star. So these are bifunctors. These are types which are indexed with two type parameters rather than just one. And both of these two are very much beyond the capabilities of Shapeless 2. I mean, there's really nothing very much that we could do to get there with that code base. Okay, but this is all still very, very low level. You would still have to write manual folds. We don't want to write folds if we can avoid it. So can we do something which is better and which is more concise and which is clearer and easy to understand? So the approach I came up with was one which tries to capture the common patterns of induction, which typically, at least for the primary cases of type classes, the kinds of type classes you see in libraries like cats, the kinds of patterns of recursion you see in those are very regular, and we can extract out common patterns which can be used to provide implementations for a significant number of these. I think actually, if you look at what's been done in the Kittens library, I think we pretty much cover everything which is provided by cats. So a derivation is possible for pretty much everything. These things, as well as eliminating the need for sort of manually written induction boilerplate, the kind of boilerplate that you might have seen in Shapeless 2 based type class derivation. It's also implemented in terms of sort of an erased kernel. We have a very strongly typed veneer, but under the hood, basically everything is managed as essentially underlying tuples of products of untyped values, but done in such a way that the implementation guarantees that types of type classes and types of components and types of the type classes corresponding to those components always line up in a safe way. This gives us really excellent compile and runtime performance, because we don't have huge amounts of code generation that the old implicit resolution induction used to give us, and indeed which the new sort of inlining model can also produce very large amounts of generated sort of inductive, invisible, but generating a bytecode footprint code. It also avoids taking a round trip through a representation type. So whereas in Shapeless 2, pretty much everything you were going to do would involve first mapping your data type into a from a case class, say, into an H list, or from a sealed trait into a nested coproduct. We can in using this model, we can avoid having to take the round trip through that representation type. So again, we eliminate the overhead of eliminate the overhead of allocations. We eliminate the memory pressure, and overall the performance is significantly improved. Okay, so what kind of folds have we got? These are the folds for products. These are folds for co-products. You'll notice there's no arguments on these, and the reason for that is that actually these are just schemas. We need to specialize these for each of the kinds that we're working with, and there really isn't a common signature that will generalize over all kinds. I mean, again, this is something which we need much more sophisticated kind polymorphism to handle. What we have instead are a set of currently for a fixed set of 4 kinds. We have well-typed veneers that sit on top of a commonly typed kernel, and here we are going to provide signatures which fully match up to the kinds of the values we're trying to operate over. So if we take an example of a type class derivation for a type of kind star, so this is going to be our ISB case. Let's try and do monoid. So this is the sort of instantiation of these folds for types of kind style. We've got a construct operator and a map to operator. So this again, this is provided by the product instances component of Shapeless 3. Construct basically will allow you to produce an element of type T. So type T here is our ISB type. So long as you can produce an f of t for each of the component types of the case class. And you can see here that we're using Scala 3 polymorphic function types to capture this in a really, really elegant kind of way. This is, again, something that was very, very difficult to do in Scala 2. And then map 2 is going to say the same kind of thing. It says, if you give me two values of type T, again, this is ISB, and a mechanism for turning a type class instance for one of the elements and a pair of the elements, so a pair of ints in this case, into another element, then it will give you back a T. So this is these are the primitives that Shapeless 3 is providing you with. And you can see how the various types line up here through the definitions. And with that in play, then this is what the whole of the derivation looks like. So this is our monoid type class. Again, this is the companion of the monoid type class. So we have a manually written instance for a primitive, but then we have the derived method here. This is going to be called by the compiler when a type declares that it derives monoid, and we're simply going to call this monoid gen method, which will produce our instance, which makes use of the instances here, calling construct and calling map2 with the body of the method filled out as appropriate for the monoid type class. I think I very nearly ran out of time, so I'm going to have to skip ahead to the end, I think. I'll skip over the functor derivation. So Shapeless 3 is available now. I just published it for Shapeless 3 release for Scala 3 final. It includes all the deriving components. There are many, many more examples in the Shapeless GitHub repository. Currently, there's a port of Shapeless 2's typable. That is probably going to go away because there is really too much overlap, I think, with the Scala 3 one. The Shapeless, as I've mentioned before, it's now moved artifact into org type level. It's going to move to the type level GitHub organization, and it now has a channel on the type level Discord, which I recommend that people join for questions. Work in progress. Well, let's talk about that in questions, and I'll leave it there. Thank you.
Hi, Miles. Thanks so much for your talk.
Hi there. I ran out of time. I always run out of time.
That's okay. Well, we do have quite a few questions, and I'd like to at least answer a few live, if you don't mind.
Let's give it a go.
Great. So our first question. For people who are new to Shapeless and want to get started using Shapeless 3, what resources or features would be the best to start with?
Well, right now, I mean, it's very, very early days for Shapeless 3. Dave Gurnell's wonderful book, The Type Astronaut's Guide to Shapeless, is for Shapeless 2. It hasn't been updated yet for Shapeless 3. The truth is that Shapeless 3 really is a completely different library from Shapeless 2. So existing material isn't going to be that helpful. So right now, it's the GitHub repository. There is a reasonably, there is some informative work in the README. There are some good examples, but this is all work in progress. I mean, we have a release, but it's it's a 1.0 release, even though it's 3.0.
Well, thank you. Our next question, why is from product so weakly typed? Wouldn't making it more type safe reduce the runtime overhead by avoiding the casts?
Well, there are no casts here. I mean, the casts will all be eliminated because, I mean, erasure is really everything. All of the types that we see are going to be erased. So the reason from product is weakly typed in that way is that there simply is no signature that could be given to it. I mean, from product is a method on a case class companion. There is no common signature that could be shared by the from product method for all possible case classes. So we end up with something which is very, very hard to work with without very, very sophisticated forms of either kind polymorphism or some kind of rather complicated encoding which carries its own kinds of costs. It's a trade-off. I would have very much liked to have a more precisely typed from product, but it's just really not possible. I think we have to kind of work with erasure on this platform, and so long as you keep the weakly typed internals genuinely internal, and I think you can do that. I mean, we certainly aimed to be able to do that. Then I think it's fine. I mean, I think we have to live with the fact that we're running on the JVM, that type erasure is something that we live with. This is an instance where we can actually use it. One of the nice things about many of the folds in Shapeless's sort of product and co-product instances type is that they are literally the same ones. I mean, once you've erased everything, because essentially we're always dealing with values. We've always got we're always taking a type and a type class corresponding to it, which exactly correspond and produce a value of kind star. So in the end, everything is a value of kind star. So we can, once everything's erased to any, everything is the same. So we don't have to duplicate anything at all. And this is actually quite a big win. I think that's my answer to the question anyway. Maybe there are other routes to making things more precisely typed, but I wasn't able to find them.
Okay, thank you. I think we have time for a couple of more. The next question is there a significant difference in compile time or runtime performance between Shapeless 2 for Scala 2 and Shapeless 3 for Scala 3?
Yes. I mean, massive.
Short answer.
Massive, I mean, it's massive performance difference. I mean, I think people need to try it.
Okay. Right. Is it possible to add Derives show on a sealed trait, or does it need to be specified for each case class?
Yes, it's defined on a sealed trait. Yes, I can show an example. I mean, it's probably best to come over to the Shapeless Discord where I can show examples. Though, I mean, there is an example in the Shapeless tests, for example.
Right. Our next question. How does deriving work for classes with type parameters where some givens are required for these type parameters, implicit dependencies?
Yeah, I had a whole big chunk of the talk where I actually showed how that worked, but I just didn't have enough time. So it works very, very nicely. It works beautifully. So the way it works is that the derived method that the compiler generates in the companion is itself, rather than being defined as a lazy a given val is defined as a given def, which is polymorphic and which can have implicit arguments. And those are the way that the implicit dependencies get threaded through into the derivation process. So it all just works. It's really nice.
Right. Well, thank you. I think we have a couple more questions. And this seems to be the last one. Can you elaborate on why it's impossible to implement the defs in sum and product in terms of the polymorphic types for all ADTs?
Because you would need to, well, because ADTs can have, say, arbitrary numbers of type parameters of arbitrary kinds. And there's no way that you can write a single method signature which can accommodate all of those possible shapes. It really can't be done. I mean, I think the only way to really demonstrate that is to just write a whole bunch of type signatures next to one another and say, well, can you come up with some way of abstracting over all of those? And the answer is no.
All right. Well, thank you. Well, I think this concludes our live Q&A. I think there might be one or two more questions that you can go ahead if you have time and just pop a reply in there if you'd like. Thank you again for your talk and for answering all these great questions. And
thank you very much indeed for inviting me. It's been great to do it. It's the first time I've done a talk for, I guess, probably for about 2 years now. It's quite unnerving.
Well, we feel very special then.
Especially virtually.
Thanks so much.